Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's video I want to introduce GeoGebra and Excel as tools to help us visualize and actually compute things relating to the algebraic calculus. In particular, we're going to be looking at areas of circles from the point of view of inscribed and circumscribed splines. So let's start with GeoGebra, which probably most of you have some familiarity with, but I'll just do a very quick review. So here is GeoGebra. It's we'll go over it very quickly. So file as sort of usual, save and open things, edit, view. There's actually quite a few different views that we're having here. On here you can see an algebra view and a graphics view. Those are the only ones that are open currently. Options, we can increase the font size if we wanted to. For example, if we wanted to make things a little bit bigger, we could make that 28. Tools, that's a little bit more specialized. We can make a new window and there's help. So over here we have various tools that are actually pre-designed. So this one helps us move stuff around. This one here, if you click on the little triangle at the bottom right, you get various options associated to this tool. So here's a tool for making points, and you can make just points by themselves, or you can make points that are already on specified objects. You can find intersections of points, or intersections of curves rather. You can find midpoints of points and a few other things. Lines, you can form unbounded lines or intervals. You can form rays, one-sided lines, even vectors. You can form perpendicular lines, parallel lines, angle bisectors, tangents to curves, and even polar or diameter lines. That's actually quite interesting for us in the algebraic calculus. So for example, let's just click on that and just see what happens. If we click on that, then I suppose we could click on the circle, and we could click on, well, we need a point, so let's make a point over here. Point. Okay, there's a point there. And now I'm going to click on that. Oh, no. So let's click on this polar again. Polar or diameter line. So maybe I should click on this one first. And then this one here, the conic. Yes, there's the polar. Okay, so as the point moves around, there's the move button. Let's get that. Now we can move stuff around. So we can move the point around, and then the polar will move. Okay, so that's actually quite an important business here in the study of conics. Okay, so we're not going to deal with that right now, but just to let you know. So over here is polygons, which we're going to find useful, and then various tools relating to circles and circular arcs. Also, hyperbolas, ellipses, parabolas, we can make them. Ellipse with two foci and a point, or similar to hyperbola with two foci and a point, or parabola, focus and directrix. And we can make a conic through 5 points. Here we can make things related to angle. We can make measurements, distance, length, areas, slopes even. Over here we can reflect and transform objects. We can translate by vectors. We can rotate around a point. We can reflect objects in points or circles. These are slider tools, so that allows us to create a parameter that's moving around. That's quite useful, and some more specialized buttons. And this last one here allows you to zoom in and zoom out of the graphic, and if you just press in here, you can move the picture around. Okay, great. Let's get rid of this point here. First of all, move. Select this point and delete. We'll get rid of that. Okay, so now we want to turn our attention to this job of trying to find an approximate area for the quarter of the circle. And I've started that by creating 5 not equally spaced points, but roughly equally spaced points around the circle. So 5 segments from here to here. And if we look at one of them, say point D, and if I right click on that and look under object properties, then we can find out a little bit about D. It's over here, but we can move that around. So let's say there. The way you import a point like that is here with this input bar. I could just type this. In fact, I could type essentially basically this thing here. And then it ends up being seen here in the definition under the properties of the point. So this is the point that we usually call E of 4/5, relating to the standard rational parameterization of the circle. So it's 1 minus 4/5 squared over 1 plus 4/5 squared. That's the x-coordinate. And the y-coordinate is 2 times 4/5 over 1 plus 4/5 squared. There's the point D. And I remind you that that's the point that you would get by going up on the y-axis to the point 4/5 and then connecting that point to the point minus 1, 0. And then that line would meet the circle exactly at that point. So that's how I've gotten all these points. I've just basically taken all these regularly spaced points here and joined them all up with minus 1, 0 to get these equally spaced points. Now let's create a polygon. There's a polygon tool. We'll grab that. Maybe actually first we should create the origin as well. So let me down here illustrate just how to make a point. Round brackets, 0, 0. Then you don't need the other one and just enter. Now you see that there's an origin G also. Okay, so we've got our polygon tool. Let's start here with click on E, click on A, on B, on C, on D, on F, down to G, and then back to E to close the cycle. And there we have a polygon. It's a cyclic oriented spline. And if we're interested in its area, which is the kind of thing that we are interested in, we could go over here to the area tool and then click on the polygon. And it would tell us that the area of this polygon is 0.77. Sometimes you can move this around. If I grab that, so I can move it around to a limited fashion. Now maybe I want a more accurate area than that, so I could right click and then under object properties I could jack up the precision. If I go to text and to rounding there, drop down to 5 decimal places, boom, I have it now to 0.77102. That's a reasonable approximation to the approximate area of a quarter circle. But it's an underestimate because this is an inscribed polygon. We'd want to bound the approximate area by also having a circumscribed polygon, and that's what we want to now look at next. Okay, so now let's have a look at inscribed and circumscribed polygons, but just for 2 points A and B on the unit circle. And we'll suppose that A is E of t for some parameter value t, and there's our usual rational parameterization of the circle. And we'll suppose that B is E of u, and here is the usual parameterization for that as well. So there's the origin, there's A, B, they form a triangle, and the area of that triangle is as an expression involving u and t, this quantity right here. It's u minus t times 1 plus tu all over 1 plus t squared times 1 plus u squared. And I can show you what that is because further down here I've got a little button here, and that's the big one. Here's the small one. So there's the area of the triangle OAB. It's 0.45616. Now the other quantity of interest is the area of the circumscribed quadrilateral. And that's what we get when we take the point A and its tangent and the point B and its tangent and see where those two tangents meet. They meet at this external point C. Now that point C has coordinates which are very pleasantly sort of a combination of the coordinates of A and B. So the coordinates are 1 minus tu over 1 plus tu and t plus u over 1 plus tu. And I remind you that's a little bit of a combination here because basically we're taking one of these forms, and instead of having t squared we have t times u. Instead of having 2t we have t plus u. It's otherwise very similar. So together with O, A, and B, we now get a quadrilateral, and that will have generally a little bit bigger area. And if the A and B points are quite a bit separated, then the difference between these two is quite noticeable. So let's have a look at the area of the quadrilateral. There it is. It's 0.86872 in this case, while the triangle is only 0.49509. So it's quite a bit of a difference. But of course, as A and B get closer to each other, then the difference between the inscribed and the circumscribed areas becomes much smaller. Now, the formula for the circumscribed quadrilateral area, here it is down here, is very pleasantly a simple relation involving u and t. So it's just u minus t over 1 plus tu. It's quite a bit simpler than the formula, actually, for the triangle, suggesting that maybe this is a little bit more, maybe fundamental. And I remind you that, interestingly, there's a relation between these two things. So if we call this second one r, so r is the area of the circumscribed quadrilateral, then the area of the inscribed triangle will be r divided by 1 plus r squared. So that's a very nice thing to remember. If you happen to know this one, then you can derive this one immediately without a separate calculation. I want to just mention a few other things just having to do with GeoGebra. So I've already shown you that these buttons here on the left-hand side allow you to reveal or hide any of the objects that you're interested in. That's very useful because if you make lots of constructions, then things can get cluttered. So we can get rid of, for example, our true things there if we wanted to. And the other thing I want to point out is that the pleasant formatting that we get here, if I right-click on one of those text boxes and look under Object Properties, so over here you'll see that there's actually a LaTeX formula capability here. So I've input an expression involving LaTeX, for those of you who know that, and then GeoGebra will automatically interpret that and give beautiful output as LaTeX does. So that's great. So now we have the kind of ingredients. We have very explicit formulas for inscribed and circumscribed splines when we just have a single oriented spline. And so now we can combine this with the previous worksheet and think about what happens when we have a bunch of points forming a larger spline, and then look at the total inscribed area and the total circumscribed area and try sort of sandwiching the area, say, of a quarter circle between them. And to manage that, we're going to go to another program. We're going to look at Excel. Okay, so here is Excel. This is Microsoft's wonderful program to deal with spreadsheets. Of course, its main application, I suppose, for most people is in terms of business and accounting and so on. But actually, it's also a very powerful tool for mathematics. And I want to illustrate some of that by applying it to this problem that we've just been talking about, of trying to compute an approximate area for a quarter of a circle. Now, that's what this particular worksheet does. It gives us an estimate of an inscribed sum corresponding to 10 points and a circumscribed sum corresponding to 10 points. And these values up here are the inner and outer sums that we get to estimate a quarter of a circle. And here, for reference, these are the actual values of pi on 4 that Excel is allowed to give us. So I want to give you a rough idea of how you can create such a thing like this, even if you're not super proficient at Excel. So let's start by having a new worksheet. There we go. It's a fresh slate. And let's start, first of all, just making some observations with Excel that obviously we have positions here indexed by columns with letters and the rows with numbers. So let's start making a table. The first entry there that I had was something like number. Let's just actually remind ourselves what the entries were. Number, t-value, inner areas, and outer areas. Okay. So number will be there, and then over here I'll write t-value, and then over here inner area and outer area. Okay, so those are going to be our headings. And what I'm going to do now is I'm going to put some numbers here, and we'll just be modest and start with 0. And then Well, this next one, I want to put the numbers from 0 down to 5, but I'm going to here make this number depend on the previous one. So I'm going to write an equal sign, which tells Excel that I'm about to create a formula. And then I'm going to just click on this previous one, so I get A6, which is the name of this cell. That's the A6 cell. And I'm going to add 1 to it. Okay, and then I'm going to press Enter. And then that becomes a 1. And if I click back on that, I can see up here the actual formula that is responsible for this 1 here. Now, an advantage in doing it this way is that if I now grab this little lower corner here, you see there's a plus sign there, and if I left click on that and I just sort of drag down a little bit, 2, 3, 4, 5, there, then it will extrapolate the formula. So if I click on, say, the third one, I see that it's A8 plus 1. So Excel is taking the formula that I used to define this one and just converting it in the obvious way sequentially down. Okay, that's great. So we've got some initial sort of points. And now I'm going to put a number over here. This is going to be the number of total points. So I'm going to put that 5, and that's in the A3 spot. Okay, now I want to, basically I want to subdivide the interval from 0 to 1 on the y-axis into these 5 different pieces. So the first one is going to be 0. And this next one, I'm going to make this, it's going to be this value here. So there's an equal sign there. And then I'm going to take this value here, and I'm going to divide it by the value here. But I'm going to do something a little bit extra, because I don't want Excel to augment this particular value. I want it to be absolutely what's in here. So if I'm going to drag this down, the A7 will change to an A8 and then to an A9 and so on. But I don't want the A3 to be dragged down to A4. So the way I'm going to do that is I'm going to put dollar signs in front of the column position and in the row position. So I have now $A, $3, and that's alerting Excel, telling Excel that I want it to use exactly what's in this cell all the time. Okay, so I've entered that. Now I'm going to press Enter, and now I've got 0.2. And now I'm going to take that 0.2 and I'm going to drag it down all the way down to 5. And you see now I've populated this column with the various multiples of 1/5. Great. So these are like the t values that are going to go from 0 to 1. These sort of correspond to the picture that I showed you in the GeoGebra slide at the beginning. Okay, so now we want to create inner areas that correspond to these. Now, if I have forgotten the formula, I could go back here and I actually could remind myself, because I could click on one of these and I could see the formula there. Right? So it's the kind of formula that has a difference and then a 1 plus a product, and then the product of 1 plus the first one squared times 1 plus the second one squared. So I'm going to replicate that kind of thing here. And I'm going to start with the first one will just be 0, and it's really this one here that's going to be the key. So I'm going to put an equal sign here telling Excel that there's going to be a formula there. So we have to write down this formula somewhat carefully. So what's it going to involve? It's going to involve these two t values, so the current t value and the previous t value. Okay, so I can click on, I'm going to put brackets, and I'm going to click on this current one, and then I'm going to subtract on the previous one and close the bracket. So that's the first factor, sort of like u minus t. Currently, this is like u, and this is like t. So we now have written u minus t. And now we're going to multiply, which we use an asterisk for that. We're going to multiply by 1 plus the product of these two. So I'm going to again click on this one to get a B7, an asterisk for a multiplication, and then I'm going to click on this cell to get B6 and close the brackets. That's going to be the numerator of the expression. Now notice that we're going beyond the cell here. That doesn't bother us at all. Here's actually the bona fide record of what we're doing. So we're in the middle of a formula. We're now going to divide by the product of two things. So I need some brackets. The first one will be 1 plus the B7 squared, and that's how you use an exponent. and then close that bracket, and then I'm going to multiply by the second factor, which will be 1 plus, oh, they found a typo. Let's see what they have. Do you want to accept this correction? I have not done something correctly yet. No, let's just leave it for now. Okay, okay. We're not finished yet. Excel, sorry. So we still have to go 1 plus B6, which is that one, and square that, and we'll close that bracket, and then we'll close up the final bracket. Now, hopefully, there should be the right number of brackets there. I'm going to press enter and see what happens. Okay, it looks like it's accepted it. Now, having the formula there, I'm going to just, again, drag that column down, and Excel is going to apply the same formula to all of these ones. So what we are having here, these are all the inscribed triangular areas that I was demonstrating in one particular case in the last slide, but one for each one of the 5 segments. You can see that they decrease somewhat, and if you look at the geometry, that shouldn't surprise you too much. Now, just to check that we're on the right footing here, I might up here write equals. I can write it also up here. Let's try that. So equals, I'm going to sum. I want to sum all of the entries in this column. So I'm going to sum, and then I'm going to sum from here. That's the first one, and then a colon down to here. And then I'm going to close the bracket and enter. And I get 0.771021. And I remind you, that's roughly the kind of thing that we had in the first GeoGebra worksheet. Great. So now we can go beyond that and actually compute a corresponding outer area. So let's see if we can do that. So there we're going to need a different formula. The first entry will still be 0. And now we have to think about what the next entry is. So that's going to be that shorter formula, the formula that was u minus t divided by 1 plus ut. Okay, so that'll be easier. So an equal sign's telling us that we're about to make a formula, and then a bracket, and then we're going to have this value, B7, minus this value, B6. That's the difference. Close bracket, and then a dividing sign, and then 1 plus the product. Again, B7 asterisk B6. Close bracket. And I hope that should do it. Enter. Okay, we get 0.2. All right, now we'll take that formula and we'll drag it down and see what we get. So if we check, for example, if we click on that cell there, for example, we see we get the same kind of formula, but it's now dealing with B10, which is this one, minus B9 divided by 1 plus their product. And to check that we're on the right track, up here we'll compute the sum of the entries in this column. That's equals sum, bracket, and then we'll tell it the cell of the first one, a colon, all the way down to this last one, and then we'll close the bracket and enter it. So we get 0.771021, and as the sort of underestimate, and 0.792722 as an overestimate. If we want to know what actually is the value, well, actually, Excel, being very smart, can tell us what that is. If we put in pi, and that's in Excel, it's a function, so if we put a function in capitals with empty brackets, then that'll give us pi, but we actually want pi divided by 4, so we'll put a pi divided by 4 there. That's 0.7853, and we could actually copy that cell, Control-C, and put it over here, so we have 2 of them. So there we can compare our underestimate and our overestimate for pi by 4 to the values that Excel has given us. So this is great. This could be done actually with relatively little work, and maybe I should save this now. So down here at the very bottom, there's a name for it, but I'm just going to save it. Rename that as 5 spline. You can't see that. Okay. But I can show you what happens with the 10 version. So the same kind of story. I just made it a nice table. I could actually go back and do that here too. If I wanted to make this a pretty table, I could just catch that there and then right click and format cells. No. I could insert table. Okay. There we go. So now we have made our values into a table. I should maybe say just a little bit about formatting. So Excel records this as a number. Here there's, I guess, 9 digits or something like that. Actually, Excel is typically working with 15 digits, 15 significant digits all the time. And what it shows you depends on your formatting convention. So we could make Excel exhibit this in a number of different ways. We could exhibit it with fewer decimal places. We could even exhibit it with fractions if we wanted to. But the underlying sort of mathematics is to 15 decimal places and not more. So we're getting pretty good accuracy, but if we want to get as good as Al-Kashi did back in the 15th century, we'd have to go beyond Excel because he computed it to more digits than that. Okay, so just to give you an idea, so then here is the same kind of computation, exactly the same kind of thing, except we've divided the range into 10 pieces, and we get a little bit tighter bounds here than the inner sums and the outer sum. And there's a worksheet here that I will post up on my in the course. So here is the version for 20, subdivision of 20. You can see we're getting closer still. And for 30. And so with this screenshot here, we have the summary of the various tables that I've created. So with 5 subdivisions, 10, 20, and 30. And here are the inner areas and the outer areas that are obtained for each of these values. And we can see that they're getting closer and closer to the approximate area of pi by 4, which is 0.785398163 to, I guess, 9 decimal places. Now, this is an interesting approximation issue. So if we actually started looking carefully at these numbers, and perhaps we computed some more of them to get the pattern more clearly, we would probably notice something. We'd notice that the inner areas are moving twice as fast, or almost twice as fast, as the outer areas. And this is something that was actually noticed by a 17th century Dutch mathematician named Snellius. And that naturally leads us to think that perhaps finding a weighted combination of these inner and outer areas is likely to be the better approximation to pi. So at first glance, you might say, well, let's just take the average of those two numbers. That's naively what you might do to approximate pi. But a more sophisticated thinking is to use Snellius's observation and take actually 1/3 of the inner area plus 2/3 of the outer area, corresponding to the fact that the inner areas are moving or progressing twice as fast as the outer areas. And that's actually quite a pleasant thing to observe. So over here, I've given you a 4th column, which I call the Snellius average. Okay, so if we click on here, for example, what do we see? The formula here, the formula is that it's B5, this one here, divided by 3, plus C5, this one over here, times 2/3. So we're taking a an affine combination, a convex combination, 1/3 of this one plus 2/3 of this one. So this is between them, but it's closer to the outer area than it is to the inner area. And when we look at these Snellius averages, we see that our progression towards pi by 4 is actually quite dramatic. So, for example, here, by the time we've gotten to 30 subdivisions, we've got 0.785, 398, 233, as compared to 785, 398, 163. So it's 6 digits of agreement, and then the disagreement in the 7th digit is only about less than 10%. So this is quite interesting and pleasant, and really shows the power of this technology. So that you could actually get a pretty good handle on pi, perhaps not having to do all that much work. It's an interesting question of just how much work one would have to do before one would get to the level at, say, that Al-Kashi was at in the 15th century. But probably Al-Kashi worked for many months, if not years, on his work. And I suspect that this approach, if you did it by hand, and it's actually quite doable by hand, because everything that we're doing here just involves basic arithmetic of additions and multiplications, so it's very doable. But I think it's a very interesting question to compare the efficiency of this method of estimating pi to the classical ones, which are almost always built up from Archimedes' original thinking in terms of estimating lengths of circular arcs. So I hope this has been instructive, first of all, to show the power of GeoGebra and the power of Excel to help us make calculations. And in calculus, we do want to make calculations. That's really important for us. And so having these kinds of tools is actually a really great advantage for us. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.